if you missed it, I think it's still open. I think it's open till midnight, actually. Most of you took it. Y'all, as a whole, like, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 A's or B's in this class on that test. So they're already in Canvas. Well, not Canvas. Don't use Canvas for grades. There it goes. Finally recording. Use Parent Portal because Canvas skews your grades. I don't always put in stuff as zeros when you don't do it. When it comes time, just make. Hopefully you know how to get to the Parent Portal. That's like a counselor kind of question, if you know. I know it was weird when I tried to get into it the first time with my kid. What? No.
Please join in as we celebrate excellence at Hazel High School. Annex and H, please step into the hallway. Everyone else come to the mall area.
If you want to go, you're welcome to go. This is too long for me to stop. I'm not anti-school spirit, I promise you. If you really want to go, you can go. All right, so what is it that this was tied into that asynchronous day opener? What is it that makes water so special?
Water?
Yes. No, but there's specific things that gives water properties. Oh, you're so close. You said hydrogen.
Oxygen.
Well, it's made of hydrogen oxygen. Okay, so yes, duh. That's part of it. But there's
Number 2.
so number 2. No, do what?
Isn't it like something to do with like surface?
It does. So water has things like, are you seriously eating a burger in here? No, wrap it up.
I'm not eating a burger.
Whatever that is, wrap that back up.
Open.
So you have things like high surface tension. You've got it has to do with the heat of vaporization, the vapor pressure. Water has certain properties because of something called hydrogen bonding. Okay, it's not between the hydrogens and the oxygen of the water, it's between the hydrogens of one water and the hydrogens of a different, or actually the oxygen of a different water molecule. They have opposite, slightly positive and negative charges, and they're sort of magnetically attracted to each other. So honestly, the secret to life on this planet is hydrogen bonds. So you're going to see this repeated over and over and over. Yes, I know this is long for notes, but most of this has been filled in for you already. So the first one, let me grab a section of this to make sure I didn't miss anything. I just This it's the hydrogen bonding within the water molecules themselves, or between the different water molecules themselves. Yeah, so it's a lot more complicated than that, but the hydrogen bonds are what causes all the other special properties that makes water so unique. Y'all, it all comes back to this particular feature. So we've got different water molecules.
It's a school shooting.
They're doing rubbing tests. There's some concept going on. I can't remember what. Okay, so if you have, boys, hush. If you have a nice, clean, and waxed car, okay, and it rains, you're going to notice that the water wants to beat up. And that's what this picture is representing. So you have different molecules of water that are actually attracted to each other. And when you have a pull to the center from every which direction, it wants to make a circle. Well, it can't make a circle because it's sitting on a flat surface. So instead it makes a bead. You can put more water into a glass than is supposed to fit. And if you've never tried it, you get just a glass and make sure it's on a flat surface. And when you go fill up the water to the top, now go get a dropper and start doing drop by drop by drop, and you actually see that it'll bulge the other way, just like this. So it is possible to put more liquid into a glass as long as it's water, because not all liquids have this high surface tension like water does. That's why raindrops look tear-shaped. So they sort of look like this. The reason why they're fatter at the bottom than the top is because of the gravitational pull, and you've got air resistance that's pushing against it and tries to flatten out that side. But it's all because of the inward pull of the attraction of the hydrogen from one water molecule to the oxygen of a different water molecule. I can't remember how well that's pictured on the notes. If I have to, I'll draw it on the dry erase board. Okay. You have things that are called surfactants. Okay, let's say you work on cars. Okay, you get grease or something in your clothes. It's just water. Huh?
I think you have to draw the thing.
It should have already been on your notes.
Just draw the water molecule and label it.
That's because you're looking at the assignment.
You're looking at the assignment, not the notes. That's why. I was gonna say, I haven't even gotten there yet. Okay, so anyways, if you get grease of some type in your clothes, is just water alone going to get it out? Y'all, listen, shh. If you get like grease or oil on your clothes, is regular water by itself gonna get it out?
No.
No, what do you add to it to make it come out?
100%.
Soap. Soap is called a surfactant. We just don't call it, oh, can you go get me some surfactant from the store? You know, you get some type of detergent or soap or something. What that does is it interferes with that attraction between the water molecules, and it lets you pull things apart. There's a phrase that you may have learned in biology that, well, did you guys learn that light dissolves life in biology? You did. Okay, so that's definitely, this is the first time you would have heard it. You have two major types of compounds on this planet. We have polar compounds like water, and we have non-polar compounds like oil. Okay, if you put oil and water together, are they going to mix? No, the oil is less dense, it's going to be on the top. And if you've never done this, you can get like an empty bottle and you put water in it, you put some food coloring in there, then you just put some oil on it, put the cap on it, you shake it up, and it makes little beads, but then they separate out. I've ever done that. Okay, that's because one is polar and one is not polar, and they can't interact with each other. That's why that happens. Water has, now this is all tied to hydrogen bonding. Water has a very low vapor pressure. That means if you have a body of water, a pond, the ocean, a puddle, I don't care. At the surface, those water molecules actually like to go into the air. They like to evaporate. If that didn't happen, we wouldn't have clouds and precipitation. Once again, this is all back to hydrogen bonding. Now, if I wish I had different colored expos, but all I have is black and orange, and the yellow needs to be. So if this is my oxygen, these are my hydrogens. Oxygen has 2 lone pairs of electrons. So now I'm going to do one underneath. Oxygen, hydrogen, hydrogen. I know you guys are probably almost done with this, and we're going to do oxygen, and then 2 hydrogens, one on this side, so oxygen, 2 hydrogens. We'll come back, and it's not exactly perfect. It's supposed to be like 4 corners, but I can't draw. Before I get to my showing of how water lines up, also has a high heat capacity. That means it takes a lot of energy to heat up water. Okay, and then if it's done naturally, it's going to take a lot of time to let it cool back off. Water is one of the best things on this planet at holding on to heat or energy. There's a reason why if you go visit the coast, your days and your nights don't have a huge temperature swing because there's more moisture in the air because the ocean is right there. But if you go to the desert, the air is really, really, really dry, and you can have 100-degree days and 30-degree nights because there's less water in the air. The more water that's present in the air, the more it holds on to the heat and the less temperature swing you have. Coasts, okay, the less you have, the easier, that's bad grammar. The easier it is to either heat up or cool off because there's less water in the air. That's why that happens. If it wasn't for all these unique properties of this, what hydrogen bonding causes, we wouldn't have life the way that we have it on this planet. Let's see here. Next one. Oh, the phase diagrams. This is great. All right, so as a whole, water has a very high boiling point. Well, like I said, most of it's filled out. You guys really have to fill in. I don't think I missed any of the blue stuff. If I did, it was an accident.
Yes, a lot of this is hydrogen bonding.
A lot of it's hydrogen bonding. It's honestly the secret to life on this planet is the way that water does this, the way that it lines up. And so we have these different, this is called a phase diagram. This is for water. Okay, so Brayden, shush. Okay, so it has a very high boiling point. Water boils, for you guys, it's 212. It's really 100 degrees Celsius because we're supposed to use metric. It freezes at 32 Fahrenheit, which is 0 degrees Celsius. Where you have a diagonal up, you're having an increase in temperature. Where you have a flat line, you're having a phase change. That means it's changing state of matter, solid, liquid, gas. This is going to be liquid. It can heat up. This is boiling, and this is going to be a vapor. While you're changing state of matter, you do not have a change in temperature. We're about to explain what's happening in each section of this. Okay, so from left to right, and I'm going to have to, I don't want to go back and forth because you guys have this on your notes. So from left to right, we're going to do A, B, B, C, C, D, D, E, and then E, F, and then we'll do the other direction. I just can't fit them both on the same slide because the type would be like itty, 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 bitty. So going from left to right, the first diagonal up, that is, in the case of ice, or I'm sorry, in case of water, that is ice. But it's warming up. It hasn't melted yet. Ice can get colder than 0 degrees Celsius. So you can heat it up to 0 degrees Celsius. But then the next line would be B to C, which is the flat line. That is the process of melting. Now going the other way, F to E was the diagonal down. That is a vapor, that is a gas that is cooling off. Once you have the flat line, that is condensation. That's what that's short for, condensation. Then going down from the right-hand side, that would be the liquid that's cooling. C to D on the left-hand side, which is the diagonal up, would be the warming liquid. Going across from the left as it's flat, that's in the point of boiling. You're not increasing temperature. The reason why you don't increase your temperature while you change states is that energy is going to break the actual bonds between the different water particles. With ice, they were totally rigid, and now they're breaking, so they're sort of loose, and then once they're loose, they're liquid. That's where the energy's going. It's not like it's vanishing. It's being used to do a purpose. So from left to right, we have warming ice, we have melting, we have warming liquid water, then we have boiling, and then we have warming steam or vapor. Going the other way, we have cooling vapor, we have condensation, we have cooling liquid, we have freezing, and then we have a cooling solid. Water doesn't hit the plasma state. That's a gas. That's like what happens in the stars. That's hydrogen gas. It's different. We normally only have the 3 base states of matter here. The only time we really see plasma is lightning. It's the only natural state that's here. What I did with my phone. I know it's a bunch. Is there, at least I think you guys were filling these in. Weren't you filling all these in? Were they already filled in? Oh, you guys are lucky. Yeah, see, I told you most of this was already done for you. How did that go for this long? Heat of vaporization is 129 joules per gram. Joule is the unit that we use for energy. Don't need, it's the energy unit. Gram would be per mass. And it's how much energy it takes to change 1 gram or 1 milliliter of water from the liquid state to the gaseous state. Now, I don't think they're going to ask you to do a lot of math with this at all. That's more pre-AP. The heat of fusion is how much it needs to go back and forth between a solid and a liquid. And for water, it's 19.1 joules per gram. I wonder if there's another one on here. No, there's not. Oh, I just pushed the wrong button. Chemistry team. All right, so this is what I was sort of trying to draw on the board. Solid ice is less dense than liquid water. Now, theirs is drawn a little bit better than mine. Okay, but what happens is when water starts to freeze, the
Hydrogen bonding, already know that.
The electrons are negative, okay, and hydrogens are slightly positive. And opposites attract. So- What now? Did we miss something? Oh, that might be on the next one. Oh, no, that's actually up for you to do. Okay, so it just says draw what atom arrangement would look like. At the solid state, they're gonna be all lined up like this. Because you have the attraction, you basically have, the ones that are in orange are not a real bond, but these are hydrogen bonds. The attraction of the hydrogen from one water's oxygen with the hydrogen of a different one. When water freezes, it makes this pocket. And what gets stuck in this pocket is air. Okay, so when water freezes, ice expands because you now have water that's in these holes that are in between them. That's why if you put like a glass jar with water in it in the freezer, it cracks and busts because the ice is expanding. That's what makes ice float. If ice couldn't float, it would sink to the bottom and this planet would be a giant ice ball forever and ever and ever and ever and ever. But it doesn't do that. But yes, hydrogen bonding. So when it asks to be able to draw, and no, it doesn't have to be perfect, but in a solid, they're all lined up. In a liquid, they've let go from each other. That looks like there's still a few of them that are still associated with each other. With a gas, on the other hand, they're all free. This is a typical water molecule. Water is known as the universal solvent. A solvent dissolves other things. Okay, the solute is the thing that is dissolved. Come back to that in a second. Water's polar. That means it's like a magnet. There's a part that's a little positive, and there's a part that's a little negative. Okay, you've got one positive hydrogen for every negative pair of electrons. So overall, water's neutral. But it has a definite positive side and a negative side, which is why it likes to line up like this in a lattice format. Gosh darn it.
Miss Rick, you know what
Yes.
a really good show you should watch?
What?
The Vampire Diaries.
Vampire Diaries? I don't know if I'm
I thought she was gonna say book.
gonna do that.
I was really into that.
No,
Our
you should
notes
watch The Vampire
backwards.
Diaries.
All right, so,
Okay,
okay, I'll take your word for it. I don't know if I'm gonna watch it though. I don't have time.
if you want to see really fine men, you should watch Vampire Diaries.
Okay, anyways, with these, it's more to understand what they look like, and I know most of this is already done for you. This is a particle of salt. Okay, salt is sodium chloride. When it's in the actual salt form, these things, this ionic compound, is bonded with each other. Okay, they're sharing a valence electron, which is why the sodium is slightly positive and the chlorine is slightly negative, but overall they're neutral. Well, if you take salt and you throw it in water, the positive hydrogen is going to be attracted to the chlorine, and the negative oxygen is going to be attracted to the sodium, and the magnetic pull of water, the polar magnetic pull of water is stronger than the attraction for the sodium and the chlorine, and that's why they separate into their ions. That's why this happens. Water is a very, very, very strong polar compound. Now, it can only dissolve certain types of substances, which is why I brought in the whole like dissolves like. Okay, I know you didn't have anything to write on that one. All right, the solvation of sodium chloride. Okay, let's see. You guys have most of this already filled in, it looks like.
Where do we put that?
At the top, at the back. The blank of sodium chloride.
So here is the.
All right, now the first one, this is all done. Like I said, the positive hydrogen is going to line up around the negative ion. The negative oxygens are going to sort of surround, they're going to encircle the positive ion. And if, as long as the polarity of water is stronger, then the attraction between the different substances in the compound, water is strong enough to pull those things apart. And it creates things called electrolytes. You should have heard of electrolytes. You need them. If you don't get them, you have a heart attack, you die. Specifically calcium. So, and I know you have the second one on here. It goes on to say that as long as the water is stronger, you'll have a pull apart. But if the compound's stronger, then the strength of the water molecules, positive and negative, nothing's going to happen. So for example, if I take chalk, calcium carbonate, regular old chalk, and I crush it up, this is an ionic compound. So you would think if I threw this in water, since the sodium chloride was ionic, that this would fall apart. But it doesn't, because the attraction for the calcium and the carbonate in this chalk is stronger than the ability for the water to be able to pull it apart. I don't know if you want to eat chalk.
They made it.
That's okay. I don't even want to know. All right. So the phrase that I brought up, like dissolves like. If your solute and your solvent are both polar, they will dissolve. If they are both non-polar, they will dissolve. But a polar and a non-polar will not mix. That's like trying to put together water and oil. It isn't going to I don't care if you shake it for 5,000 years. You set it down and they're going to separate. Similar to how a lava lamp works, by the way. Except there's heat involved in a lava lamp too. Okay, so we have 3 more. That said, vocab lessons are way longer than math lessons. Okay, crystal structure. Water, as a hydrate, a lot of times crystal's a solid. Well, water's a liquid. In a crystalline structure, in a hydrate, which I don't know if I have any back there. I'll go and look real quick. But hydrates have water attached to them, but they are not in a liquid state. They are in a solid state. Let me go see if I have some hydrates. I'm there. I'm down. I thought maybe I could show you the way it's on a bottle, but we don't have any back here. You would have your compound, okay, and then it's going to have something hydrate. Hydrate means water. How many is di?
2.
2. So this is cobalt is +3, chlorine is -1. So this is the cobalt 3 chloride dihydrate. This is a little multiplication dot that's in between them if you can't see that. I don't know if it's on yours or not. It's not. So it would be like this. Let me erase my water. You want the water. So, since it's a little hard to see it, so you would have the cobalt 3 chloride, CO, Cl3, you have a dot, and then it's dihydrate. The one on the right, sodium sulfate, Na+1, sulfate's -2, crisscross, multiplication dot, deca is 10 waters. If you have a hydrate, they are once again not in the liquid state, they're in the solid state. Two more. Yes, I know. Vocab. Do y'all still need this one? Those hydrates, whether it's a monohydrate, trihydrate, tetrahydrate, I don't care. They're known as a water of hydration. Efflorescence is what happens when they lose those. It no longer has those water molecules that are attached into its crystalline structure. If you have something that reduces moisture, if you've ever noticed when you get like shoes or even now with like certain medications, they have these little silica packets in them. It says do not eat. And if you open them, they look like little balls of like hard plastic stuff. You know what I'm talking about? That is a hygroscopic compound. It's keeping moisture out of it so that in the case of shoes, they don't get moldy and stink. And in the case of most medicines, you get moisture in with your medication and it's It's gonna like melt the pills, if you will, like the statins and whatnot. I know I don't get those little things in my statin cholesterol medication, but I do in my blood pressure stuff, and I don't know why. One's apparently more sensitive to water being present than others. Commonly, these things are known as desiccants. If you have something that's desiccated, it's like dried out and mummified. That's what desiccation means. But the whole purpose is to keep the water from affecting whatever the substance is that it's with. We got one more.
Don't change it yet.
I'm not changing it yet. I'm going to check online, actually. Don't want to sit on my phone. Sorry. I still only see that glove.
No.
When we're done with this, and then you have to go to A-Hall because, and we did get an email, if none of the other teachers told you, that we are not allowed to unlock bathrooms if we have a key to the multi-stalls. They said that there are single-person bathrooms somewhere on campus, and you should be using those.
Wait, what?
I don't know. We got an email yesterday, late in the day, about not opening the multi-stall bathrooms.
Wow.
I don't know. You guys know better than me. Vaping, vandalizing, doing naughty things with each other. I've heard all different kinds of stories.
Well, I know you do it all the time.
All right, so,
Why
shush.
did you?
So,
That's you,
hey,
Jay.
delinquent. Shh. Hush.
What's the hair?
Hush. Delinquent compounds.
What are we talking about?
People being bad. Now hush. Delinquents. They pull water out of the environment so well that they end up normally turning into a liquid because they've pulled so much moisture out of the air. I know you guys hate that word, but sorry, I'm gonna end up using it. When certain things dissolve in water, like salt, it makes it much easier to run an electrical current through it. Pure water actually does not like to run an electrical current. No, shh. It has to have electrolytes suspended in it to run electricity, which is why they're called electrolytes. Non-electrolytes don't like to conduct electricity. So electrolytes include strong acids and bases. Y'all, very soon we will be doing acids and bases. Enjoy the simple math while we had it. We're not going to blow anything up. Oh, there's a space there that shouldn't be there. I'll fix it. Things that are insoluble in covalent compounds, when you throw them in water, they don't actually help run an electrical current.
Oh god, I messed up.
You messed up?
Yep.
How?
Places and things.
It goes right in order. And then the last part, it says in what ways, I mean, the first one should be obvious. What? What? Where? What?
It's not going to put the or however they pronounce that, compounds where electrolyte goes, and I put electrolyte where non-electrolyte.
So scratch it out and right above it or next to it or under it or something. Right on the bottom. Okay, I know what the first answer is going to be. In what ways do you use water in your life?
Drinking.
Obviously, for hydrating
Wash
yourself,
my
washing things. We use water all over the place. Cleaning things. How do water's physical and chemical characteristics make it suitable for living systems? How does water carry nutrients through our body? In our blood? How? How does it get, obviously that you eat and you drink and it goes down into your intestines and then it goes across the intestinal wall. Okay, and then the water portion of our blood is going to pick up the nutrients, but how does it pick up the nutrients? What is water's fingers, if you will?
What was that?
It's that slightly positive and slightly negative. It's that polar nature of water. Most of the things that our body needs to survive are called electrolytes. They're either positive or they're negatively charged. Water has the ability with its oxygen to grab onto positively charged ions, electrolytes, and carry them through the blood. Whereas its hydrogen, which is positive, has the ability to grab onto negatively charged ions. So chlorine would be that case. The sodium would be the case for the oxygen. If water could not carry these electrolytes, I'm telling you, without calcium, you have a heart attack and you die. Without sodium, your sodium potassium pump doesn't work.
Maybe I'm.
Your kidneys fail. You literally, like, your cells will bust because you cannot pee water out. They can't be processed by the loop in the kidneys. Without water's ability to be able to do that, to pull things apart, like almost magnetically, you would not be here. So, I mean, I've had people, well, what's the secret to life? And I'm like, water? And they're like, that's stupid. And I'm like, well, it's true.
So the answer is what?
Water.
Water. It's the way water works. Okay, now I know that this is a whole bunch of vocabulary for you guys in order to do. It's not hard. Let me freeze this and let me stop the recording because I don't want to, it's